And then there's nasty trig. We're doing all of it. What? Nasty trig and nice easy trig.
I'll talk about it really, but okay.
Oh, I'll get to that.
Well, should we give it to us over the weekend?
I know, my fault. But it's such an easy task.
I don't have
Wait,
time to
you
do it
mean
at night
this?
because I gotta work all
You
night.
mean this test?
Huh?
Do we not have a test review?
Yeah, I know. You want now?
Sure.
Yeah, because I don't want you working on it all QT. So, angles. Definition.
Distance from the x-axis?
They call it an initial point, but I'm going to call it a start point. Angles are formed by two rays that share a common starting point, an initial point. Everybody remember what a ray is?
Yeah.
What's a ray?
Has a dot at the
It
end.
has a dot and it has an arrow, and it goes off for ever in that direction, which is different than a vector, which if you ever take physics, you'll learn.
Oh, no.
Actually, you'll learn vectors in here. So, if this is our initial start point, and this is one ray, going off forever in that direction, and another ray starts at the exact same point and goes off in a different direction. They could go off in the same direction, but that'd be kind of boring. It would be an angle that actually has zero measure, because they'd be going in the same direction. We consider the separation of these two as an angle. Ooh, angle. Angle. Now, I normally denote my angles as theta. Greek letter time, theta. So I might as well show you all the Greek letters I'm going to do. This is alpha. I don't do omega. Beta. Theta. What else do I use in here? I think those are the major ones for here. So just trying to get used to Greek letters because they crop up every once in a while. Other ones I get used like in calculus, delta, epsilon. I think are the two major ones for calculus. So we're going to be talking about angles. Now, when I think of angles, since like my daughter doesn't know how to read an analog clock, this probably means absolutely nothing to her.
What?
Analog clock, you know, with hands
Yes, I know how to
and
read
quarter
those.
of and all that fun stuff.
I can't read those.
Yeah. So I always think of angles as the separation of the hour hand and the minute hand. So as the minute hand moves, the angle is getting bigger. Now clocks actually go backwards to the way we're going to measure angles. We're going to standardize it a little bit, and we're going to put the angles in a coordinate system. So we're going to put it in an XY plane. And we're going to choose one side to always be part of the angle. So this is called the initial side. It's where we're going to start forming our angle. So it always goes off on the positive x-axis. When we open an angle, it goes opposite of a clock. A clock opens clockwise. Angles open counterclockwise. So when we're talking about moving an angle in the positive direction, we're going to be talking about opening them in that direction. So we're going to separate the arrows and open up our angle in a positive direction, counterclockwise. And we'll get this other side up here, and this will be the terminal side. And of course, this will be our angle theta in between. Now, theta is measured in degrees commonly. What's a full rotation in degrees?
360.
Why?
Because it is
Who the heck chose 360? Why not 100? Why not 50? Why not 25? Why 360?
360 days.
For a long time, the world thought there was only 360 days in a calendar, and they used angles mostly to study the sky. So the sky changed in a 360-day period because the stars would shift as we went around the sun.
What about leap year?
Okay, If they only had 360 days in a year, they definitely didn't know about leap year. Because there are technically 365.25 days in a year. Oy. So 360 degrees was associated with the number of days in a year. And it became archaic and it's kind of boring and you can't use calculus with degrees. So we have to kind of switch it over into something else. So a quick little review. If you're on the initial side with your terminal side, your measure of your angle is 0. I don't care where you are. If you're pointing straight up, 90. If you're pointing to the left, 180 degrees or a straight angle. If you're pointing down, 270. And if you come all the way around, 360. I go backwards.
That's a -90.
That's -90 because you're now pointing down, but you've moved in that direction to it. So -90 and positive 270 are exactly the same angle. Those are called coterminal angles. So if they wrap around, you can wrap around as many times as you want. As long as you stop someplace, you can measure it many different ways.
So it's like a unit circle.
Oh, let's not even talk about
What's a
unit
unit
circle yet. Let's not even get there yet. I don't like unit circles except for one piece. So if I have an angle that is 538 degrees, 538 degrees, how do I find its position? Well,
Subtract 360.
you know you're going to be going around, and it's bigger than 360. So one thing you know for sure is this angle is starting here, and it's already wrapped around once, guaranteed without a doubt. So that coterminals with the initial side to begin with, so I can get rid of 360 degrees. What am I down to? 538 minus 360?
It's 178.
178. So the coterminal angle with 538 degrees is 178 degrees. What quadrant is it in? It's in the second because it's bigger than 90 and smaller than 270. So it's someplace over here. You don't have to draw them perfect. And it's wrapping around to here. So it's the same thing as if we just did 178 degrees to start with. What if I went backwards? How many degrees is from the initial side backwards to the terminal side?
Third quadrant.
Yeah, but what would be this measure? How would you find it?
Oh.
-2, 360 subtract 178.
Oh God, that would be horrible.
I don't know what's going on.
If I want to go this direction,
-360 plus 178.
-360 plus 178 would get you to the answer. Because you're going -360 and backing off 178.
Yeah.
182.
182,
Negative.
negative 182. So this would be the same thing as -182. So there's got to be a neat formula that can get you to these coterminal angles. And it pretty much works out this way.
Of course.
Theta and beta are coterminal. Basically, if and only if. Theta can be written as beta plus 2k pi. Or beta could be equal to theta plus 2k pi. Either way works. Where k is an integer. So k can only be 1, 2, 3, 4, or -1, -2, -3, -4, or 0. 0 would be perfect because then theta would equal beta directly. Sound good?
What determines K?
Depends. Like 538 here, to get to 178, k was -1. See? Oh, did I put 2 pi?
Yes.
My fault. My brain's in radians. 360k. 360k. I teach so much calculus that 2 pi is much more natural for me. We'll talk about pi in a second.
K.
K is just an integer.
Anytime
It's
it
like
goes
-2, -1, 0, 1, or 2. So if I have 73 degrees and I want to find a coterminal angle, I can take it and add it on to 360 times k. Now, if k is equal to 1, I just add these two. If k is equal to -1, you subtract these two. If k is equal to 2, you're doing 2 loops and then adding 73 degrees to it. So it just always lands wherever the heck 73 degrees is, no matter what k is equal to, as long as k is a integer. It has to be an integer.
So what would the answer be?
For which one?
What the coterminal?
Oh, a coterminal angle? Let k equal 1. So you get 73 plus 360, which would be, what is it?
433.
433?
I think so. 423.
423.
No, it's 4.
So 423
Yeah,
degrees.
433.
433.
33.
Okay, someone make up my mind.
433.
33.
33. Great. We all know how to add. Another one would be 73 minus 720. What would k equal there?
That's negative 3.
Why'd you get 720?
That's what I'm asking. Where did it come from?
Negative 3.
Negative 2.
Negative 2.
Yeah,
2 times 360
Oh,
is
yeah.
720. So this would be, when k is equal to negative 2, we get this coterminal angle, which is negative, I don't know,
647.
647.
Okay, cool.
And that would be another coterminal angle.
Wait, does it map? Can you plug in any integer?
Yeah.
And it'll be a coterminal?
Coterminal angle, yeah. That's the beauty of that formula.
So
Guaranteed.
we could get all kinds of answers for that.
You can get infinite number of answers
So-
for that.
Theta is always 73.
The angle itself, the smallest angle, you usually try to go for one between 0 and 360. The smallest angle itself is 73. But working with 433 and negative 647 will give you all the same answers. Because they're technically the same angle. They're in the same location, first quadrant, 73 degrees up. Does that make sense? You want me to draw pictures? I can draw pictures.
Wait,
So
so
it doesn't.
Like, 73 degrees is like here. This would be 73 degrees. The first one, adding 360 to it, all you're doing is you're starting here, and you're looping it around and coming up there. So that would be stopping the angle at the exact same place. If you subtract 2 of them, you're just going backwards twice. And you're stopping there at the exact same place. So it's still 73 degrees, it just has different numeric values. But it's exactly the same angle. That's the funky thing with angles, because they could wrap around. Like clocks are constantly wrapping around themselves. How many times has a clock gone around since the beginning of clocks? A lot. Not time itself. I was just talking about when they invented the clock. It's going to be a lot of times wrapping around. Every, 24 times every day. The minute hand goes around. Okay. So we need to change things into something called radians.
You don't do that.
Yes, we do. So this is extremely important. Everything I do basically works in radians. I very rarely go back to degrees. The only time I go back to degrees is solving like word problems. I want to know how many degrees an elevation is. I'd rather work with degrees than radians. So radians is defined to be this. If you have a circle centered at the origin, and it has a certain, radius, let's give it an r, and we make the radius the angle. We extend the radius beyond the circle. Then this angle theta here, and this arc length s here, and r are related by a nice little formula. So we choose the measure of angle of theta. We choose this ratio. Theta is equal to the arc length divided by the radius of the circle. Now, the nice thing about this formula is if the radius was measured in centimeters, you'd have radius like, let's say 5 centimeters. And let's say the arc length was 10 centimeters. The answer would be 2. Not 2 centimeters, it would just be 2. So when we change things into radians, it becomes a unitless measurement. Has absolutely no unit associated with it. No feet, no inches, no meters, nothing. And it's much better than degrees, because if you do a calculation in degrees does not go away. You have to keep it as a unit. So this becomes what's called a unitless measurement. So this formula is very powerful. It has two versions. You can write it this way too. This is called the arc length formula, and this is called the radian formula, depending on what variable you're solving for. We're going to be solving for theta. So if I have 90 degrees, I want to know what the relationship is between 90 degrees and theta. So I'm going to look for theta. If I'm dealing with this circle here, and 90 degrees brings me up here, how much of an arc length did I cut out of my circle?
Oh.
I don't want to talk about pi. It's a fourth of the circle, right? It's a quarter of the circle. So it's 1/4. How do you find the circumference of a circle?
2 pi.
2 pi r. So it's 1/4 of 2 pi r divided by the radius itself, which is r. The cool thing is, what happens to the r's?
Cancel.
They cancel out. 1/4 of 2 is
1.5.
1/2. And then you have a pi. So this breaks down to pi over 2. So 90 degrees in old language is now going to be pi over 2 in new language. All right, so what if we go 2
Pi.
cuts? It'll be pi, it'll be double that. So 180 degrees is the same thing as pi radians. Well, I'll write RAD, but eventually I drop that because it is unitless. 270 degrees.
2 pi.
It is not
No,
2 pi.
3 pi.
It's a 3 of these, so it'd be 3 pi over 2. And then 360 degrees is 2 pi. Because it would be 4 of those, and 4 times 2 pi over 2 is 2 pi. These are the main ones you need to know. 90 is pi over 2, 180 is pi, 270 is 3 pi over 2, and 360 is 2 pi. So what if I have a weird measured angle, like 40 degrees? How am I going to convert it? So let me ask before I ask that one. Something similar. If you have 75 miles per hour, might as well learn how to do this. I need to convert it. In physics, we need this thing to be feet per second.
Meters.
I have miles up there. I'm not converting it to meters. So, to do a unit conversion, you're going to multiply by a bunch of fractions. This one's going to be long and ugly. The degrees to radians and radians to degrees is easy. So the first thing I'm going to choose to get rid of is hours. I want to change this into feet per second, FPS. So, how do I get rid of hours? Well, it's in the bottom here, so I'm going to put it in the top here. And then I want to change it into seconds. How many seconds are in an hour? There's 60 seconds per minute. And 60 minutes per hour. 360?
140.
1,000.
No.
3,600.
3,600. 3,600. So there's 3,600, 3,600 seconds for every single hour. Now this fraction that I just designed equals 1 because it's talking about the same measurement. 1 hour, 1 hour. All right, so that'll get rid of the hours. Now I want to get rid of the miles. So the miles is in the top here, so I'm going to put it in the bottom. And I want to change it into feet. How many feet in a mile? 5,280. 5,280 feet in a mile. That's why it's better to work with kilometers, meters, centimeters, and all that fun stuff.
Can you put the 5,280 over to 1 hour? In minutes?
Please no. Yes, you can, but not for your reasoning. So the hours are going to cancel. The miles are going to cancel. Oh, by the way, that's 1. And all you're left with is feet and seconds in the bottom, which is where you want it. So you can say per second. So it's 75 times 5,280 divided by 3,600.
110.
110
Yes.
feet per second. So if you're traveling at 75 miles per hour, you're driving along 64, going 5 miles per hour over the speed limit, like most people do, you are actually traveling 110 feet every second. So if a deer runs out in front of you, and it takes you a second to take your foot off the gas and put it on the brake, are you going to hit that deer?
Yes.
Heck yeah. Because number one, you're going to travel 110 feet, and that's quite a distance if you think about it. Number two, you still have to have braking distance, which is another 110 feet or so. So yeah, you're going to hit that deer. I don't care what you do. So you might as well just hit it.
Did it.
Unless you are really
Swerve.
like James Bond swerve type guy.
I can do it.
But this is what's called unit conversion. So I need a unit conversion to take 40 degrees and change it into a radian. Because I can't just keep breaking it up this way. I guess I could, but it would get kind of messy this way. So what I want to do is I want to take 40 degrees and I want to multiply it by something. Well, what I want to multiply by has a degree in the bottom and a radian in the top, and it equals 1. Just like 1 hour over 3,600 seconds, or 5,280 feet in a mile.
Would you put 360 on the bottom?
Well, you could put 360 in the bottom if you want, but I like other ones. Look, you could use 90 and pi over 2, but then that's a fraction. You could use 360 and 2 pi, but then there's a common factor of 2, so you might as well use 180 and pi. It's the one that has no common factors and it's not fraction in form. So I'm going to use pi radians and 180 degrees. They mean the exact same measurement in angle measurements. It's a straight angle. So what happens to the degrees? They technically cancel. What's 40 divided by 180 in fraction form? This is where that ABC button or math enter comes in handy. 2/9? So this is the same thing as 2 pi over 9. Leave the pi there. There's very few reasons to get rid of the pi unless the number in front becomes a decimal and then you just multiply by 3.1428, whatever it is. Does that make sense? It's not too hard. Go for it.
What if, like, for some reason, they were asking for the angle itself, and they asked you to find?
That's the angle, that's the angle.
No. Like if they said x times some random radians on top, and then an angle on the bottom. How did you find it in intercepts? And it
You have to
wasn't.
change one into the other.
Wasn't one of those four.
Ask me later. I don't know what the heck you're talking about.
Wait, can you explain why you chose 180?
I need them to be equal. Like I know that there's 3,600 seconds for 1 hour, 3 feet for 1 yard. So I want something to equal each other, and I know for sure that 180 equals pi. So if I put them over each other, they'll equal 1, and that's the important thing. They need to equal 1. Has to be a unit conversion. So what if I start off with 7 pi over 12? Now this is written in radians. Once you see a pi in a number, it's usually assumed to be in radians. If it was a decimal like 2.13, I either have to tell you it's in radians or if it's in degrees. If it's in radians, I'll write RAD, but technically you're not supposed to write that. So how would I change 7 pi over 12? Well, I'd multiply by a fraction. It's in radians, so the radians would have to go in the bottom. That's that pi thing. And in the top would have to go 180 degrees. So the pi's are going to cancel. You get 7 times 180 divided by 12.
105.
Yes.
So this is 105 degrees. 105 degrees. Now the only time you would have to be, well, messy with this is if I said, what if I have 2.13 radians? Then you can't get rid of the pi because 2.13 does not have a pi in it. So you're still going to multiply this by 180 degrees over pi and change it into a decimal degree. Decimal degree. So what's this turn into? I don't know. It would be 2.13 times 180. Then you have to use your pi button on your calculator. So divide by pi. Some ugly number.
1,220.04.
122.04.
0.01.
Yeah.
And this would be in degrees. Thank God I don't have to teach you degrees, minutes, and seconds. Because very few people use degrees, minutes, and seconds anymore. Engineers, I would imagine, use it, or road construction crews, or surveyors might use degrees. Oh, you don't know? Huh? Oh, I'll teach it. Degrees, minutes, and seconds. Why not?
So what?
Hey, we don't
We don't need to know this.
Wait, hold on. What'd you do? The last one again?
What did I do on this one?
Yeah,
You
Just
teach
this
about
times this
how-
divided by pi
No, you can't.
as a decimal. So you change pi, use your calculator pi.
on the car.
Yeah, use your calculator pi.
He watches Japanese.
What, so,
Oh, so you don't.
He watches them.
He does not.
What?
if you have a pi on top, like 7 pi over 12, you would do 180 over pi.
This is in radians already, so if you want to convert it to degrees, the degrees has to be in the top. That's the reason. It's not the reason that I put pi in the bottom to cancel this pi. Because I could write something like pi degrees, convert it to radians, and if you cancel the pi's, it's wrong already. So you got to be careful. If you want to change it to radians, radians is in the top. If you want to change it to degrees, degrees is in the top. In this fraction. In that fraction. So you can flip it, which is kind of cool. Degrees, minutes, seconds.
I
Better
thought
know.
you just said we didn't need to know it.
I'm giving it to you anyways.
Wait, so.
Just in case you do need it. I don't know where you're going. You could find a job as a surveyor, you never know. Degrees, minutes, seconds. So if I give you 43 degrees, 12 minutes, and 38 seconds. All this means is this. This is old notation again. Degrees was like years. This is minutes and seconds like time. So they kind of combine a few ideas. This is the same thing as 43 plus 12 over 60 plus 38 over 3,600 or 60 squared.
It's quiz time.
Yeah. Minutes and seconds.
Oh.
There's 60 minutes in an hour and 60 seconds in an hour. So in your calculator, if you just type this in, you get your decimal degrees, or better known as DD. So 43 plus 12 over 60 plus 38 over 60 squared equals 43 point
It's just
2-1.
43.21.
21.
No, that's everything.
Everything, all of it.
43.21.
Just 2-1. And this would be decimal degrees. So where this is degrees, minutes, and seconds, this is decimal degrees. It's just different ways of measuring it. Most of your calculators will do this conversion with a button. There should be a DMS button and DD button. DMS to DD? Yeah, it is.
Negative. Negative dash, right?
Where is it? If you hit degrees,
Yeah,
where's
I
time
see.
of this
No,
way?
I got it.
I didn't know what you do with that.
I don't know.
What do you
That's
mean?
why I always do it longhand.
Oh, there it is.
I see it.
Converted to back.
Yeah, it's in there.
Where'd you go?
Where'd it go?
I'm sorry. Oh, you-
Where's catalog?
Where's catalog? It's under angle.
What's angle?
It's under the button angle.
Where's angle?
I don't know. It's on there someplace. Don't worry about it. It's not a big deal. It's not a big deal.
Oh, I found it. Email.
Yeah, it's in there. DMS and DD.
Where's it there?
So why is it DD?
Decimal degrees.
Why decimal? That's what I'm asking.
It's in decimals. See, this is in fractions. This is in decimals. Converting angles. Great. Arc length.
Hey,
It's quiz time.
What?
It's most.
It's only 2:20.
It's quiz time.
They don't
Close. Let me get my little application out of the way. It's very short. Oh no, it's not very short.
Yeah. It's
I can get one of them out of the way.
What the?
Did she just get angry?
Yes.
How horrible.
What you done for here? Angles.
Oops.
Quiz?
It's just a problem. In a circle, that's not too bad. With a central angle, that means it emanates from the center. And the measurement of this angle is 30 degrees. And the radius is 12 centimeters. And we're looking for the arc length cut by this angle.
Oh.
So we're just looking for this piece, the length of that arc. It's not a straight line because it's on a circle. The formula I gave you earlier is this. It's a very simple formula, but you've got to be really, really careful with it. If you type in 30 times 12, you're guaranteed the wrong answer. Because theta, this formula comes from theta equals S over R. What's theta measured in? It's definitely not degrees. That's the definition of radians. So when you see this formula, that theta has to be in radians. So the first thing you have to do is convert 30 degrees to radians. So it would be 30 degrees times 180 on the bottom and pi in the top, because you want to change it to radians. The degrees goes opposite direction. So what's 30 over 180? Well, that's a sixth. That's 1/6. So this is pi over 6. It is the same thing as 30 degrees. These are some of the things you're going to have to memorize eventually. 30 degrees is pi over 6. 90 degrees is pi over 2. So forth and so on.
Are you gonna tell us that?
No, you need to know these eventually as we go through this chapter.
Would you, and for this chapter in mannerisms, should our calculators be in radians or
Depends.
degrees?
So this becomes S equals theta, which is pi over 6, and the radius, which is 12 centimeters. Now, because theta is a unitless measurement, your answer is going to be in centimeters. So you type in your calculator, literally, pi times 12 divided by 6. And you do need the pi in there to get the right answer. What is it? 2.5?
2 pi?
Five.
What?
No.
6.
Pi times, oh, I see, 2 pi, yes, so 6.28.
6.28.
How boring.
Can't you like go on your calculator and put like 60, find the degree thing, and then put that in? Okay, never mind. Never mind.
Stop it.
Well, I just did that and came out as the same answer.
Quiz time. You're an angular velocity. Most people understand linear velocity. They get very confused with angular velocity. So when you talk about velocity or rate of change, when we talk about velocity, we talk about it as an instantaneous thing. So we're going to keep the speed of these things constant so we can talk about it as velocity. So when you talk about linear velocity, the formula distance equals rate times time comes into play. Distance equals rate times time. So as you're traveling around, we're going to be traveling around a circle. We want to know how fast we are at any point on the circle. Like if it's a record, remember old record players? Does anybody
Yes.
you know,
Yes.
little 45s?
Yes.
They call them 45s because they revolve at 45 revolutions per minute. So it keeps track of it. And the songs on the outer edge go quicker, and the songs on the inner edge actually go a little bit slower because as you move in, you're slowing down.
It's on there. I've always wondered it.
What?
I know what song it was on when you put it up. Was it there?
You just there's gaps.
Oh, really?
Yeah, you
I
can see
remember
the
looking at
gaps
it.
between
I
the
remember
songs.
looking
So
at
you
it.
put it on the gap.
Oh, okay. It's pretty neat.
That's old folks. That's old folks.
You would answer that one.
I would not.
I feel like you know what Green Acres is too.
So when we're talking about a circle, Green Acres, my lord.
What?
When we're talking about a circle and we're moving from this point to this point, how do you measure the distance you travel? How do you measure the distance you traveled?
Can't
You
you
can
do
use
the
the
thing?
S equals pi.
Use that S thing.
Yeah.
So S is
Theta.
involved,
Theta.
theta is going to be involved, and so is R. Now we're doing linear velocity, so that means we need to solve this equation for R. We need to solve it for R. So we're going to get R is equal to distance over time. So for this one, we're going to get V is equal to, we'll call it velocity directly. V is equal to distance. Well, the distance covered is
RT.
S.
S
Oh yeah, yes.
over T. Now S, by formula standards, is also known as theta R. So we can also write it as theta R over T.
Hey, sign it right.
I might actually have to look at the notes. This is sad. Hey, okay, so far so good.
So,
Or this for us.
I'm sort of going along and trying to learn from last chapter, or from
Well, I haven't.
what y'all did the other
I
day.
didn't teach them anything except for
Theta R.
S is
S
theta
equals
R.
theta R.
Okay.
That's and the definition of radians is theta equals S over R.
I'll just watch the video.
Okay.
Watch it on YouTube.
It'll get there. So when we talk about linear velocity, this is the formula we're going to use. One of those two. If we know what S is, great. If we don't, we can use theta R. Now T is how much time has
Aren't you looking for R?
passed. No, we're going to be given R.
All the
I mean,
time.
we could be given, as long as we're given two of the pieces, like, if I'm given V and T, I can find S. If I'm given V and S, I can find T. If I'm given S and T, I can find V. So, usually you're looking for velocity.
But you're not that simple. You'll make it smart.
This is actually simplistic. Angular velocity is a little different. So we're going to call this omega. No, that is not a W. That is the Greek letter omega, like alpha and the omega.
Looks like it's like a cartoon, but
So
Nice.
omega is going to be the rate of change in the angle with respect to time. So how fast is the angle changing as time goes on? Is it a slow opening angle or is it really quick? Like a door or a record player, or the difference between a 45 and I think the other one was like 30. I can't remember, it's been so many years. So what we can do with these two formulas, this one's nice, except for one problem.
what is that?
I can do a little substitution here. Where can I substitute?
You can multiply the T over.
You can do
and
W
you can-
theta equals T.
WT equals theta.
Yeah,
Yeah.
that's what I was thinking of.
Oh, yeah, right here. I have theta over t.
Yeah, that's what
I'm getting there. So we can also say that omega is equal to, velocity is equal to
So
Omega R.
Sorry.
omega r. So that's a similar formula. Now, the only thing that you have to be really careful with is angular velocity is usually measured in things like RPM. Angular velocities is usually, it's not in angular velocity language. That's the problem with RPM. This is what, revolutions?
Rapid.
No. Per minute. If you have an odometer, no, what's it called on a car? Tachometer. If you have a tachometer on your car, it measures revolutions per minute. It says 5, but it means 5,000. So when you get your car up to 5, its revolution of its drive shaft is 5,000 times every minute, which means your engine is going to, basically blow up. Okay, so revolutions per minute, and what we're going to do here is use this idea right here. In a circle, one revolution measures how many radians?
Wait, what?
In a circle, one revolution measures 2 pi. So every time you see revolutions, you're going to times that by 2 pi. And that changes it right over into an angle. This will turn into theta. So it's RPM times 2 pi will give you theta.
That's the time from Eric's.
What's that?
That's the time from
That's the times, yeah. Revolutions per minute times 2 pi will give you your theta. So if you're doing 2 revolutions per minute, well, it'll be per minute, theta per minute. If you're doing 30, what did I say?
Oh no.
I forgot. If I'm doing 5 revolutions per minute, that means I'm going through 10 pi radians every minute. This is omega. Why? Because omega is change in your angle over change in
You just
time.
said that theta is what that is.
I forgot. Revolutions times 2 pi is theta, but this is revolutions per minute. So I get that per minute in there and I get omega out of it.
Oh, okay.
See, just the revolutions times 2 pi just gives me my angle. But if I take the revolutions per minute and times it by 2 pi, I get theta per minute, which is omega. Phew. So we could do a simple problem. Oops, wrong problem. Let's do this one. For example,
1 plus 1.
1 plus 1 is 3.
There's actually
I bet it's-
2 plus 2 equals fish. 3 plus 3 is 8. Yep. 7, 7. Fine.
This was off Twitter or Facebook. You all read off of.
7 plus 7 is
It's about 6 inches.
What?
A 35 record has a diameter of 6 inches.
Why was he going like this?
That's about the size of a 35 record. Not that big, about 6
They're
inches.
small.
Yeah, they're very small.
One of the flags
Oh, 45 record, I'm sorry.
What are you doing?
Stop changing it.
I'm sorry. A 45 record has a diameter of 6 inches. How fast is the outer edge moving? Question mark.
As fast as you want to.
So a 45 record, which has 45 revolutions per minute. Stop whispering.
I like to whisper too.
Has a diameter of 6 inches, and I need to find out how fast the outer edge is moving. So here's your record. The outer edge is any point on the outside, and as this record moves, I want to keep track of how fast that one point is moving on the circle itself.
He has a diameter.
So the diameter of 6 inches, what's the radius? 3.
3.
So change that right into 3 inches. The 45 revolutions per minute, we're going to find omega from. So we're going to say omega is equal to
45 times 2 pi.
45 times 2 pi. And this will be per minute. So that turns into 90 pi per minute. So that's our omega. Don't change it to decimal form, just leave it as 90 pi.
Alright.
So this is the angular velocity of that point on the record, the one on the outer edge. Then we want to change it into velocity. Well, velocity, the simple formula is omega r. So the velocity of that object is going to be 20, or I'm sorry.
Wait, okay, hold on.
You're
You're
going
going so fast for me.
I am?
Yes.
Oh.
Alright, okay. Alright.
All right.
So, over here you get the form with RPM x 2 pi. What is x?
Times. That's not x. My x is this.
Can you do it?
Dot.
Yeah.
Thank you.
Dot.
I appreciate it.
This is my x.
Okay.
Okay.
That'd be lovely. That'd be great.
It's the RPM that I don't like putting a dot there for, but. So can I start over here again?
Maybe.
Yes.
Omega is 90 pi. The radius is 6 inches.
Right.
The radius is 3.
The radius is 3, buddy.
Well, someone said 6.
No, that's
Oh,
the
the
diameter.
diameter.
I swear. So you get 90 pi times 3. This is inches, and it's every single minute. All right, so this turns into what as a decimal?
Why? Wait.
I don't know how you
How would you put that in?
calculator.
What are you trying
You
to
don't. You just go 3 times 90 times pi.
My calculator.
3 times 90 times pi.
Pi.
848.
848.23
.23
and 2 inches per
minute.
minute. Does this mean anything to anybody?
Definitely not.
Heck no. So guess what we're going to do?
Great.
Stop
Make a
there.
new one.
We need to change it into something we recognize.
I think it's fine the way it is.
What
Yeah.
speed do we recognize?
Your body looks great.
Feet per hour.
We do not recognize feet per hour.
Miles per hour.
Miles per
I
hour.
want to do feet.
So I need to change
Oh, Lord.
feet. I'll give you feet. I need to change 848.2 inches per minute, and I want to change it into miles per hour because I don't know what the heck 848 inches per minute means. So what
Sounds like
measurement do you want to get rid of first? Inches?
Let's go to inches.
So if we get rid of inches, we put inches down here. What are we changing it to?
Why would you put it?
Because the inches will cancel.
I'm sorry, I take that back.
What do you want to change it to?
Miles.
Do you know how many inches are in a mile?
No.
I don't
They
either.
told us. They told us. I just don't remember.
It's 12. Really? They told you?
Whoa.
Ugh. 12 inches for every foot.
63,000.
Oh my God. We'll get to it.
Shush you.
So what do I want to get rid of now?
Feet.
Feet.
Calculus.
So put feet down here. Put miles up here. How many feet in a mile?
Come on, Sam. You know this one.
5,000.
5,280
Boom.
for every single mile. 5,280 feet per mile. Now, we've got it in terms of miles, that part. We're done with that. Now we just got to get
Gotta get that baby in there.
hours. So how do I get rid of minutes? Put it at the top. What am I changing it to?
6.
Hours down to the bottom. How many minutes in an hour?
60.
60. So your calculation is 848.2 times 60 divided by 12. Take that answer, divide by 5280. In other words, multiply by the numbers that are in the top, divide by the numbers that are in
That's what I
the
was just gonna do.
bottom.
It's like stoichiometry crap.
Yeah.
What?
Stoichiometry.
Stoichiometry.
What is that anyway?
It's like that crap that we did in chemistry.
Chemistry, bubble.
You trying to kill someone?
Oh my god, I hated chemistry.
I love
Awesome.
chemistry.
It
Crossed
made me,
the line.
it just made my head hurt.
So what's this turned into?
I loved everything.
If you
until
give
Mr.
me
James came
a
in.
minute, por favor.
Well, if you weren't talking por favor,
Hey, that's the whispering right there, not me. Alright, it's 0.80.
0.80.
32. Well,
So 0.80 miles per hour. So not even 1 mile per hour. Not even. Pretty close though. You could walk faster.
Do you have to change it to miles per hour?
I will ask you
I feel
to.
like some people on the road drive that speed. People in Rocky Mount can't drive.
thinking on old people?
Yes.
Old people.
Oh, like
Let's make it a little harder.
it's 40, not 45.
Let's talk about a bike
What's that?
and how the heck it actually works. So here you have the pedal. Is it E-L or L-E?
A-L.
A-L?
Pedals your pedal.
A-L.
Pedal. So here's your pedal. Let's say your pedal has a gear that is about 3 inches. Let's say that, 3 inches. With those little sprockets on it. And connected to this is a chain, of course. And the chain goes down here to a smaller sprocket. Down here. Let's say the radius of this one
Oh.
is 1 inch. So you're going from a 3-inch pedal to a 1-inch gear on your back wheel. And then your back wheel is attached to that. And let's say it has a radius of 24?
What kind of bike is this?
I don't know, just making it up. It doesn't really matter.
It's like a Whoville bike?
What, 3-inch? It's a gear, 5-speed. I don't know. It's a 26-inch wheel. It'd be a 13-inch radius, right?
Well, if it's kind of flat here.
That's what my bike is. I'm tall, so I have to have a large wheel.
I got a beach cruiser.
Okay, so depending on how fast you pedal this pedal, it spins the gear a little bit faster, and the gear spins the entire tire, and that determines the speed that your bike is actually going, because if we can find the linear velocity of that point on that wheel, we would know how fast our bike is going.
I'd rather use physics.
I don't want to know how
I would
fast
rather
our
use
bike
physics.
is
There's no
going.
physics to this.
I'd rather just skip.
So,
Yeah.
let's say that this wheel here, the pedal, we're pedaling this thing at maybe 3 revolutions per minute.
I
3
covered my
revolutions.
mouth.
That's
You don't have to do that. Revolutions per minute.
Revolutions per minute. Well, no. Make it,
Yeah, that's kind of small.
yeah, let's make it 30.
Wow.
30 revolutions per minute. We're going really slow.
Yeah, it's like,
Well,
it's like,
we're going up the hill, okay?
I was trying to think, yeah.
Let's go.
That wasn't even,
You're driving a
if
Prius.
you had 3 revolutions per minute, it
You're
would be
driving a
like,
blue Prius.
Yeah.
It sound like-
But 30
Afraid
might
of
even be
riding
too
bikes.
slow.
I really am.
Yeah, make it 70.
Yeah.
Get
out of the way.
70 revolutions per minute. Now we're on a motorcycle. now. So, if this thing is revolving at 70 revolutions per minute, what determines how fast that chain is moving?
The chain's gonna go faster.
Well, when there's
You just
It's
said-
linear velocity.
question.
Alright, sure.
Okay.
What?
Wouldn't there be like friction against?
Stop it. So,
Can't.
there's this point on the chain that we're going to keep track of, and it's going to be going a certain velocity around our pedal. That's going to determine how fast this chain is going to be moving, because that chain is attached to that point. So, how fast is that point moving on the pedal itself? Well, I know that this thing is doing 70 revolutions per minute. So what's the first thing I need to do to 70 revolutions per minute?
Times it by 2 pi.
Times it by 2 pi.
40 pi.
So this turns into omega equals 140 pi per minute. So the speed of this point, which is also the speed of the chain, is going around with an omega of 140 pi per minute. What's its velocity?
145.
Like completely or just 3?
Well, just in pi form. It'll be 140 pi times
3.
3. So that turns into,
1319.460.
no decimals. Keep it in pi. Keep
Where'd
it
you
in
get
pi.
120?
70 times 2 pi.
420 pi, sir.
Remember, you take this and you multiply by
2 pi. 2 pi.
It'd be 420 pi.
420 pi. So the linear velocity of the chain is 420 pi.
Of that one.
Of that chain. This whole chain is moving around
But you don't want
at 400 pi inches per minute. If you really want to be precise.
You want the other one.
I'm getting there, but you can only do one piece at a time. So,
Excuse me?
next thing we need to look at is the tiny gear. What I know about the tiny gear is its linear velocity is this. It has to be traveling at 420 pi inches per minute.
Did you say initial?
Huh?
Stop it. I did not say initial velocity. This is not physics class. Okay. So this thing is doing 420 pi per inches per minute as it revolves around. From that, can I find out its angular velocity?
Good.
Well, we have a formula. The velocity is equal to omega times r. Which piece do I know?
Velocity.
Both of them.
I know the velocity. This is 420 pi. Do I know omega?
Yeah.
For the big circle, yes, not this little one.
Ah,
So omega. Do I know the radius of my little
Yes.
One.
1? So omega is directly equal to
420 pi.
420 pi. So for the little circle, omega is equal to 420 pi.
There had the same omega.
how nice.
Okay.
Wait,
What?
so
I have one more circle to go.
I know, but is it always like if
Oh, well, if the radius was 2, then it would cut this in half.
Yeah.
If the radius was 0.5, it would double this.
okay.
So that's what happens when you have a gear. When the gears get smaller, when your chain comes down on the gears to a smaller gear, it actually makes the angular velocity twice as fast, or a fractional fast, than the original speed. All right, now for this big circle that is attached to this small circle that shares a common center point, what is the angular velocity of this point way out on this circle?
420.
420, because it's the same as the angular velocity of the little circle. So this is the angular velocity of the big circle. So I can set up v equals omega r. I know omega is 420 pi. What's the radius of my big circle?
13.
13 inches.
So you wouldn't add the 1 inch?
Yeah, I was saying we're gonna add the 1 inch.
No. It's 13 inches from the center of the circle all the way out. When you have a 26-inch wheel, it's just half. It's 30. This is the one I need in decimal form.
17,153.0
That's close. That's good enough,
or
trust me.
0.1.
0.1. That 0.1's not going to do us any good. Now this is inches per
Okay.
minute.
I can get it. So
Now. I need to convert inches per minute into miles per hour. Same calculation in the green up here. You're going to multiply by,
60.
so 17,153 times 60 divided by 12.
16.
Wait,
So I gotta write-
I'll write it down and do it. 2.
Sorry.
16?
Yeah.
16.2.
Yeah.
So this is the same thing approximately as 16.2 miles per hour. And that's how a bike works.
Okay.
16.2. Maybe they're wrong. No, Nick's wrong.
That's bad.
Mine's
I'm
correct.
It's not that
Six.
fast. 20 miles per hour.
How you doing?
Bikes, if you're pedaling really hard, you could probably
Like driving
get it up to
down
about
hill.
30. Probably get it up to 30.
Unless you have one of those speed bikes.
Unless you're a professional, yeah.
Speed bikes.
So you said that times 60 and divided by 12.
Take that answer and then divide by 5280. Don't do 60 divided by 12 divided by 5280. I'm not sure if it'll give you the right answer.
Yeah, I got that one.
I don't trust calculators that far.
Scoop that up.
I don't trust them that far. All right, so that's it for angular and linear velocity. So the only things you really have to remember about angular velocity is take the revolutions per minute and multiply by 2 pi. then the linear velocity is easy. It's just omega r. Just omega r. Guess what formulas I don't give to you on the test?
Those.
And
I
I
have
do.
this.
And I
The top
love
thingy?
this problem.
Do you give us the top thingy?
Top thingy.
That thing?
The converter?
This stoichiometry
Oh,
graph?
this?
Yeah.
Do you need that?
That's in your
I don't
brain.
know the miles.
You need to know 5280 feet per mile.
Yes.
58 to
5,280, sir.
5,280. What did I say? 58? All right. One of my favorite problems of all time. There is a shortcut to this. If you can find it out, great. There is a relationship between the three circles.